Welcome everyone. Time for our next session, and this one is titled Resilient Foods for a Future-Proofed Foods System, presented by Juan García Martínez. Juan obtained his Master of Science in Chemical Engineering from the University of Twente and went on to join ALLFED as a research associate. His work at ALLFED focuses on assessing the potential of various technologies for production of food resilient to global catastrophes. So Juan, I'm delighted to welcome you to the stage, and I'm going to hand over to you.
Thank you for the introduction, Beth. Let me share my slides. And here we go. So I'd like to welcome you all. I'd like to add that if you have any additional questions or you'd like to connect with me for a collaboration or something after this, you can connect at this link in the slides, allfed.info, there at the bottom, allfed.info/FFPS 2022. So let's start. First of all, a few clarifications on the type of work that we're doing at the Alliance to Feed the Earth in Disasters. There are plenty of potential catastrophes in the world, as we have been made painfully aware of, but we're focusing on the ones where within this rectangle here, which has been broken down into three different categories depending on the severity of the food shock that we're dealing with. First off, we have plenty of global disasters that could reduce or produce a food production loss on the order of 10% of the global food production, including abrupt climate change, volcanic eruptions, and many others. And a report for the UK government has estimated a chance of this happening of around 80% on this century, so it's very significant. Going forwards, in the increasing order of severity, we have several potential mechanisms for a collapse of critical infrastructures, whether regional or global, that could affect food production and distribution significantly. Here's what's represented here as loss of industrial civilization. And finally, on this category of global catastrophe, on the order of magnitude of near total food production loss, there are also a few mechanisms that could, or types of catastrophes that could cause this to happen. And that's what we're going to be talking mostly. First off, some clarifications on this collapse of critical infrastructure. There are different risks that could cause this, affecting food production significantly. For example, coordinated nuclear high-altitude EMP attacks that would destroy circuits, electricity production facilities, transformers. An extreme solar storm, maybe like a 1 in 10,000 year solar storm, could cause very significant damage. Or cyber attacks, which have been increasing in the last few years. And because of the interdependence in the system, it will affect food fuel production, energy production, transportation, supply chains, and finally, food production and distribution. But mostly we're going to be focusing on a different type of catastrophe that could cause near total agricultural food production loss. And that's what we call these abrupt sunlight reduction scenarios. The mechanism over there is, and you can see like the main things that could cause that is like a large comet or asteroid impact, a very large climate-changing volcanic eruption, or a nuclear war causing a nuclear winter. The mechanism for that is that the burning of cities or the very large amount of aerosol material emitted by the impact or the eruption would get lost into the atmosphere, significantly reducing the amount of solar irradiation or sunlight reaching the surface of the Earth, which would also significantly decrease surface temperatures and precipitation. And when you put this all together, you can expect a significant food production shock from there. Depending on the severity of the scenario, and you can see different increasing severities in this graph on the bottom left here, from top to bottom, you can see that in the most extreme scenario studied, the loss of food production could reach between like up to 90% of the total global food production, which would be almost total food production loss. Now, this is a very extreme scenario, but even in this scenario, there are things that we can do to prevent mass starvation around the world. And that's what our work focuses on. What we work on is work on resilient food solutions That's what we call the foods that would allow us to rapidly counter this loss of food production in a way that is, fast enough to counter this before famine becomes widespread, and also in a way that's affordable for the populations that are most at risk to be able to have access to these foods. So here's a sample of different foods that I'm going to be discussing. We're going to be talking about like fermentation-based foods like single-cell proteins, seaweed cultivation, cool-tolerant crops, which can withstand the reduction in temperature, and greenhouses. I've divided the set of food production of resilient food solutions that I'm going to be discussing in between low-tech or high-tech, more industrial type of food solutions. And first, I'm going to discuss the low-tech ones. This thing I'm showing here is a seaweed cultivation system, which very well qualifies as low-tech. As you can see, it's little more than ropes and buoys and some boats that you need to cultivate the seaweed there. This would allow you to cultivate seaweed, and seaweed grows very fast. It grows like between 3 to 20% dry mass per day, which equates over the longer term exponential growth, which will allow you to cultivate a very significant amount of food in very little time, and also at a reasonably affordable cost. Here's a map that we created for one of our projects showing the suitable US area near the coast and harbor that would allow for seaweed cultivation in the extreme nuclear winter scenario. As you can see, there's plenty of area available. And here on the bottom, this is a ramp-up speed, as we call it, which is simply on the y-axis, the amount of production. In this case, it's given as a percentage of the human requirements, the human food requirements, and on the x-axis, the time after catastrophe strikes, or rather after you decide to start ramping up these solutions. And you can see from the graph that we would be able to reach a huge amount of food production, like about 3 times as much food as needed, which could be used like for biofuels or for animal feed or for many other uses, in addition to feeding some of it to humans. You cannot survive only on one food, naturally, but this shows the huge production potential of seaweed for responding to this type of catastrophes. Another thing that would be very highly impactful to avoid famine would be relocating cool-tolerant crops from the northern hemispheres, where they are being grown now, to more tropical latitudes, where they would have the right climate zones to grow and after the catastrophe has stricken. Some of these foods or these cool-tolerant crops that we think are most promising at the moment include rapeseed oil, and which is one of the few sources of fat that we would be able to probably in the most extreme scenarios grow. In addition, barley, spring wheat, some winter wheat as well. Potatoes are also famously cool-tolerant, turnips, beets, and so on. Another high-impact intervention would be the deployment of simple low-tech greenhouses, little more than plastic layers and sticks to hold them in place, that would create chambers that increase the temperature inside and also increase the growing degree days, or the season that you can grow the vegetables in, which would potentially allow you to increase not only the yields after a catastrophe, but also would potentially allow you to grow vegetables in places where you will otherwise be unable to. In some scenarios, yes. These are mostly large-scale centralized interventions that I've been discussing. There are also other more community-level or decentralized food production interventions that could be applied in these scenarios. Like, for example, there will be plenty of inedible plant fiber lying around from dying trees and leaves, and there are many different things that you can do to turn those into food available for humans. So, for example, you can grow mushrooms on the trees, or grow or have dairy cows feed on grass and leaves that are left and produce milk from that, which is much more efficient than producing beef, as you probably know. You can also have fiber-eating insects that can digest these cellulosic materials as well. And finally, from some leaves, you can press them and produce a leaf protein concentrate from them that is also very high in some nutrients, for example, vitamin C, and would also be very useful and can be produced at a community level scale with limited technology. Now, moving on to the other category of resilient foods, these are what we call the industrial resilient food solutions or the high-tech resilient food solutions. It's mostly the idea of deploying large amounts of factories to produce food production independently from agriculture, or to repurpose existing industrial infrastructure to produce from producing something that is not food, which is what it's doing right now, to producing foods. So the first one I wanted to talk about, well, the first thing that we need to talk about is what resources would we have available to produce food independently from agriculture. And this is these are the ones that I'm going to be discussing now. First off, there's this lignocellulosic biomass, trees and leaves that you can process into foods. So you may also be surprised to learn that you can turn all of these different fossil fuels separately into food by processing them chemically and biochemically. And finally, you can take CO2 from an industrial point source, of which there's no shortage, or directly from the atmosphere via direct air capture, and also use that as a chemical building block to produce food. I'm going to be discussing those food sources and how you can turn them into, those resources and how you can turn them into food. But first, a few words on of the resilience of these high-tech systems. Their closed environment makes them immune to climate variability and change, which is why they're such a good bet in these scenarios. They can also be built modularly, such that if one of the units breaks, the rest are still working. And they can be deployed in a polycentric manner by having multiple different factories in different places, such that there's no single point of failure in the system. So in those are all the senses in which the resilience of the food system is increased by applying this high-tech food production system. On the other hand, the resilience of the system to disruptions to the energy and supply chain systems is decreased, for example, to the risks that I was mentioning earlier, cyber attack, EMP, solar storm, due to the huge interdependence in the system that will cause what we call digital fragility and reduced resilience. So you win some, you lose some. The food production systems in particular that we think are most promising are, for example, this process to turn lignocellulosic wood into sugars via a chemical and biochemical treatment. Here you can see the final product, how it would look from a company called Renmatics that has been producing this. Here's an approximate, here's a simple model trying to estimate how fast you could ramp up this food production system by not only building new factories to convert these trees and leaves into sugars, but also by repurposing existing infrastructure such as pulp and paper factories or breweries or biorefineries that we already have, and switching some of the units around, adding some new ones, and using them to, from turning them from a bioethanol or paper factory into a food production factory to produce sugar, which you can then directly use as human food or feed it to a fermentation tank and producing something more nutritionally interesting, or as animal feed. The other very highly promising industrial resilient food production system that we've studied is not single-cell protein from methane or from natural gas. By feeding our bioreactor, as shown here, with an oxygen source, like from the air, and a nitrogen source, such as ammonia, and methane, which these bacteria can digest as their carbon source and their energy source, from which they get the energy and the atoms that they need to build their own proteins. And you produce a significant amount of bacteria or other microorganisms. You separate that and dry it, and you can produce a protein powder looking like this, very high with very high nutrition quality, like very good amino acid profile and nutritional properties, and high digestibility as well. Or you can try to texturize that or post-process it into something more palatable or more attractive for consumers. The cost of doing this, of course, this protein powder, we estimated that at like between $1,000 to $2,000 per ton in terms of production cost. In normal conditions, in a catastrophe, it will be more expensive since we're assuming that we will be building these factories 24/7, and we would expect $2 to $3 per kilogram cost, but it would still be widely affordable for the global population. There are many other food production systems that are high-tech that you will be able to use to respond to such an extreme catastrophe. For example, you could use like photobioreactors or closed environment agriculture system. Unfortunately, these are generally not very energy efficient. There are other more energy efficient alternatives that are being developed right now, such as artificial synthesis of carbohydrates, such as sugars and glycerol, which you can do without any biological organisms at all. Or alternatively, do these biosynthesis like the single-cell protein production that we were talking about from CO2 directly, such as solar food is doing, or air protein, or do bioelectrosynthesis to have electricity eating bacteria produce things like fatty acids. Putting all these things together, we are modeling the scenario where we're comparing what would happen if we were to do very little adaptation to this extreme food production shock versus doing a lot of adaptation, include producing a significant amount of these resilient foods. And that's the difference between this top graph and this bottom graph that you can see here. In the top one, you would at most be able to feed 30% of the population if you would not be able to produce any additional resilient foods, but an effective rapid resilient food response with rational stock management and rapid culling of animals would allow for increasing that number from having at most 30% of the global population surviving to producing even more than the minimum amount of requirements of the population, which would still be less than we're producing now, but would mean that technically no one would need to starve, assuming an adequate political response. So that's the end of my presentation. If you would like to volunteer or collaborate externally, please contact me in this link, allfed.info/FFPS2022. We need people from diverse backgrounds, including engineers, agricultural economists, programmers, data scientists, and also please feel free to check our website. Thank you.
Juan, thank you so much. We do have some questions coming in, so we'll dive into those. So someone says, leading up to 2020, governments were repeatedly warned that a global pandemic was likely. Yet when COVID struck, the world was largely unprepared. What, from your research, should we be most concerned about in terms of risk to future food security? Climate change will be a slow burner.
Yeah, that's a good question. So it's something that keeps me up at night. Even if we have technological solutions to respond to a very diverse set of catastrophes, including biological risks and agricultural risks like these ones, without the adequate level of preparedness and resilience at the institutional and private industry level, there is little that we can do. If people do not decide to deploy the technologies at the adequate pace, then they would simply not be of much use, which we saw happening in many regions during COVID, unfortunately, yes. Climate change is also a concern and would certainly, and that's what the UK government in that report I mentioned was mostly concerned about, could cause a multiple breadbasket failure.
Got it. Thank you, Juan. So another question. Some of the scenarios you described at the start were frightening. How hard is it to build awareness so that governments, communities, and individuals can take proactive steps to ensure they're ready to hit the ground running if a disaster does strike?
Yes, excellent question. It has been, I would say, in my subjective experience, hard to raise awareness on institutions. Thankfully, supranational institutions like the UN have been paying more attention to this type of catastrophes, even though their capacity to act is limited to what their separate governments want to do. But governments generally do not like to look at tail risk or extreme type of scenarios. So there's been less traction at the national government level, but some traction at the supranational level.
Okay, and we'll just take one more quick question from Nick, who says, how seriously do governments take these catastrophic risks to humanity that you've talked about?
So the short answer is not much. Generally, governments are more concerned with recurring disasters rather than with disasters that are unprecedented, as we are all painfully aware of. We've seen what happened in COVID, and we can expect probably worst pandemics in the coming in this century. So yeah, that's a short answer.
All right. Thank you so much, Juan, and thank you for everyone watching. If you did have additional questions for Juan, I know there was a couple that we didn't get to in the chat box, please do drop Juan a message directly through the platform. I'm sure he would love to see those. So we have one more solo presentation to go, and then one final panel discussion coming up, which will bring us to the end of day one. So please stick with us, and we'll see you on the next session very soon, just in a couple of minutes' time. See you there. Bye-bye.